It's fine. Yeah. Yeah, just put it. Sure. So, shall we start?
Okay. Yeah,
good. Hello, my name is Xinyu from the University of Queensland. Today I'll present our ADCS paper, Robustness of Neural Rankers to Typos, a comparative study. This is a joint work with Shengyao, Zhuang, and our supervisor, Guido, Zuccon. Sorry. So when you come to Adelaide, South Australia, where it's famous for its winemaking, you probably want to taste some wine, say Shiraz, and then you just type it carefully in the search engine. Usually it works successfully, and returns information of Shiraz to address your need. But it's common for humans to make mistakes. So, and you may miss an H and you guess a SIRAZ. And actually, it returns Shiraz, which is the capital city of a province in Iran. So in this case, the information need cannot be addressed properly with typo query. So we wonder what happened inside the search engine. So one of the recent neural information retrieval paradigms for query and document matching is dense retrieval. It uses fine-tuned pre-trained language model, for example, BERT, to get dense representation vectors of queries and documents, and then computes the similarity scores for retrieval. These pre-trained language models are therefore called dense retrievers. So one typical example is dense passage retrieval, or DPR, which is a BERT-based bioencoder. And so consider that case where you type Shiraz in it will be encoded by the dense retriever into for example, 512, typically 512 dimension vectors, and you just to compute the similarity between those two vectors for the similarity. And different from dense retrieval, sparse retrieval is another neural information retrieval paradigm. It also uses pre-trained language models, but the goal is to improve the term weighting or the sparse representation of the queries and documents, typically by expanding the documents or computing new weights for terms. So an example of sparse retrievers is deep impact. So here you put Shiraz, and you will get presented in vectors, but they are based on the index or vocabulary of the corpus which used to be searched. And therefore, it's usually a high dimensional and sparse representation compared with the dense representation we just discussed before. And you see here, you have very clear meaning of each dimension, but for the dense retrieval, for the dense presentation, you probably don't know so which each dimension means. Yeah. And current neural sparse retrievers can actually span the documents. So they're, for as you say, from the right side. So they do like some reweighting of the documents. So the group, you say the grape, Shiraz, and it's not 0 or 1, it's actually 1 or 3, they are real numbers. Yeah, kind of. Previous work has investigated robustness of two based models, DPR and monobert, for passage ranking on typo queries. So these typo queries are derived from mathematical depth queries with generated synthetic typos. And both of them have observed significant loss in effectiveness. And interestingly, DPR as a dense retriever has the largest loss, making its effectiveness almost on a par with that of BM25. So we are firstly to look at the dense retrievers and how do they perform on the typo queries. And then in this work, we propose that data augmentation approach called Typos over training. So just simply and working together with typo generators. So it works like for each query in the training epoch, it has 50% chances to have a typo being ejected by one uniformly sampled typo generator. And therefore, the model can learn from both queries and with and without typos, and minimize the training loss, so such that it will be robust to different types of typos. And evaluation on queries with and without typos show that typos over training provides around 55% increase for the dense passage retrieval on typo queries and keeps the same effectiveness as traditional training on typo-free queries. So in this paper, we're interested in the performance of sparse retrievers on query with typos, which has not been largely explored yet. And upon that, we include more retrievers and consider state-of-the-art ones, as well as for both and sparse, to see if these recent advanced retrievers are robust to typo queries, and whether there is a difference between these two kinds of retrievers. And we also test if the typos of training a data augmentation method originally proposed for dense retrievers can be generalized to sparse retrievers. So first, to see whether dense and the sparse retrievers are robust to query with typos, we follow the previous work as introduced before in generating synthetic typo queries. And because there's no large-scale data set that has enough queries with typos and associated labeled passages available, and we had to resort to synthetically generate it. And the synthetic typo query generation involves queries that don't contain typos from 3 data sets. So mathematical, passage, ranking, development query set, the track, DL 2019 and 2020. So specifically, we're using 5 realistic typo generators. So as you can see from the right side, and so for each query in each data set, we randomly sample a word from the query, and then generate a typo by randomly sampling a typo generator and applying to that sampled word. So the generated typo queries share the same relevant passages with their typo-free ones in our setting. So what happened when you put these typo queries into the dense retrievers? So see here, actually, the queries first presented text will be tokenized, and here, like you can see, they are tokenized into different parts, and that may cause actually the difference in their embeddings here and if you put that into a sparse retriever, and actually they do exact word matching, so that's actually the Shiraz one. Actually, if you're lucky enough, you can find one, and it leads you to that map to that Iranian city. But if there's no Shiraz in the vocabulary, so we'll probably get nothing, and failed. So to run the experiment, we consider the following retrievers. For dense retrievers, we use an ENS, Disturber TSB, TCT Cobalt with V2, and co-condenser, which is the state-of-the-art dense retriever. And And for sparse retrievers, we regard the traditional BM25 algorithm as a classic bag of words zero-shot sparse retrieval model, and plus document to query T5, deep impact unicoil, and the spread V2, which is state-of-the-art sparse retrievers. So for later, we will to studying whether typos over training works, we will compare with co-condenser unicoil, Tilde V2, and the spread V2. And as introduced, so co-condenser and the spread V2 are the 2 state-of-the-arts for dense and sparse retrievers. So let's see how they perform on the original queries. So for dense retrievers, we can see sharp decreases of the effectiveness of all models once typos are introduced in the queries. Interestingly, also ENS has the lowest effectiveness amongst the considered dense retrievers on the original typo-free queries. Here it displays the highest robustness to typos, even outperforms stronger dense retrievers on queries with typos. It is true, and for other dense datasets and metrics. Hence, we find current state-of-the-art dense retrievers are not robust to type queries. And then we turn to sparse retrievers. So similar to dense retrievers, the effectiveness of all the models sharply decreases. We also know that the impact is more effective than doc-to-query T5 before typo introduced. And this is statistically significant. However, when queries with typos are considered, deep impact and document-to-query T5 achieve the same effectiveness, and similar observations also found on other datasets and metrics. Hence, we found current state-of-the-art sparse retrievers are also not robust to typo queries. And now, so we conclude the current state-of-the-art and sparse and dense retrievers are not robust to queries with typos. So dense retrievers exhibit slightly higher robustness than sparse retrievers, and among them, Nth shows the least degradation due to typos. And we further want to know, does typos over training work this time? So for fair comparison, we retrained these models, and the results on original typo-free queries shown that typos over training is less effective for tilde v2 and unicoil. The improvement for queries with typos is marginal. When comparing to the original training, tilde v2 and unicoil trained with typos over training achieved lower effectiveness. This is a statistically significant difference. And in contrast, typos over training appears to work well for split v2 and co-condenser when used on queries with typos, both split v2 and co-condenser trained with typos over training, except to no statistically significant difference. Hence, we conclude that typos over training has little effect to tilde v2 and unicoil. And then we turn to the typo queries. So typos over training is less effective for tilde v2 and unicoil. The improvement for queries with typos, it is notable that although typos over training is less effective for tilde v2 and unicoil, the improvement for queries with typos is marginal when compared with the original training. And tilde v2 and unicoil trained with typos aware training achieve lower effectiveness, and this is significantly significant. But it is notable that although tilde v2 and unicoil and split v2 or sparse retrievers, we obtain considerably different results when comparing tilde v2 and unicoil with split v2. Typos over training is more effective for split v2 than that for tilde v2 and unicoil. We argue that this is due to the fact that tilde v2 and unicoil only have a passage expansion step as data processing strategy before training. So split v2 learns how to expand queries and the passages on the fly during training. Hence, so it's able to learn a query and passage expansion pattern that tolerate the typos in queries, whereas tilde v2 and unicoil cannot. And split v2, split v2 without typos over training also does not provide an expansion of this query that contains the correctly spelled terms. It is then logically that the improvements provided by typos over training on split v2 are significant when in presence of queries that contains typos. Hence, we found that the augmentation-based typos over training is effective to improve the robustness of the current state-of-the-art sparse and dense retrievers, say split v2 and condenser to typo queries. To conclude the paper, we contributed a comparative study of the effectiveness of sparse and dense retrievers on queries with typos. With this respect, we found that both sparse and dense retrievers are not robust to typos in queries, and the sparse retrievers are generally more sensitive than sparse retrievers. We also evaluated a data augmentation-based typos over training method, which was previously shown effective in making dense retrievers more robust to queries with typos. We applied this method to the sparse retrievers, and then we found that this training method is effective to make the co-condenser more robust to typos and queries. And however, when applied to the sparse retrievers, tilde v2 and unicoil, we found the typos over training is less effective for queries with typos, and it slightly hurts their effectiveness on queries that do not contain typos. And these findings more generally suggest that typos over training could also be effective for sparse retrievers, if the end-to-end query and passage expansion strategy is used during training. And for future works, more effective typos over training method approach is needed. And well, these typos were, and for the data, which, because you recall we use synthetic typos in the data. And those typos actually realistic, but they only consider errors made with respect to insertion of this kind of things. And we don't consider the phonetically compatible misspellings. Like for the same sound, we have different spellings due to orthography kind of thing. And we also only expand the possibility that we just inject like one typo in the query. So what about we inject multi-typos? And also we didn't consider like typos in other languages like Chinese because they may have different patterns. And for our payment code, please check the link and the QR code. And thank you for listening. Any questions?
Thank you. Thank you. That was really interesting talk. I have an observation. Maybe I've missed something. I have an observation to make leading to a question. And the observation that I have to make is that humans are actually really, really good at spotting and understanding typos. It's not a problem at all. In fact, humans can read complex texts where all of the letters of the words are mixed up, apart from the first letter of the word and the last letter of the word. Humans can do this without a problem. Yeah. And it's because we recognize the shape of the words generally. And so my question is it typos that are the problem, or is it tokenization schemes that are the problem?
Yeah,
because
that's interesting.
If you were simply using the words as images, the actual word and the typo word will be very similar to each other.
Yeah, exactly. That's a very interesting question. So do you mean here, like for I showed this in the tokenization, you find some like you're wondering so if there's something problem in the tokenization function? I think it's due to the vocabulary. Like for actually, I use BERT to do this case. So BERT don't have so much vocabulary, so he can only introduce tokenize this into these forms, which he may be more familiar with. So the problem for this because it's due to the vocabulary of the pre-trained language model is not that large, which is compatible to humans. And I also I think that yeah, that's a very interesting question. Like maybe we can discuss it later.
Hey, thanks for the talk. It's really interesting. I have a question about the method that you used. Did it had also a negative effect on some of the queries? Because we saw the average, but were some queries negatively affected by that training method? Because I'm not sure, but if I understand this example correctly, these two are valid queries, but for different information.
Yeah, indeed.
So if you train it to
exactly. So this is just a toy case, which is not precisely like to show the typos in real life, but it can also be considered as one kind of typo to be shown here. So actually, you can refer to a paper which we have actually more better example, like which cannot be shown properly or beautifully, but you can on the mathematical data set you can Thank you.
Very good speech, Xinyu. And I enjoyed the presentation, but I have a question. Let's say in this, I have a query, right? Instead of typing in God we trust, example, in dog we trust. It could be true, but the question is that would we able to know that it's a typo, or this, like, what happens in that kind of scenario? It's like,
so you mean if the typo is not in the query but in the document?
No, it's in the query. So I want to search. My intention is like, okay, so I want to trust, like, okay, in God we trust. I just want to understand the motor, but I type in dog we trust. It could be my intention is that I trust the dog. Could be, yes, but my original intention is in God we trust. Because generally these are not two typos. I'm not making a typo. It's not like Shiraz, but they have two different intentions. So
you mean while we think about something, but we type in another thing? Is that the case? Yeah. Well, that I think that is too complicated for language models for ALP models, because they can't read your minds. I think is so right. So it can only understand what the input or what you give them. Right? So I think if we can inject some knowledge into the models, that could be much smarter.
Any other questions? No? Okay, let's thanks, Dave.
Okay, thank you.